Hello and welcome everybody to our today's webinar. I quickly want to introduce the team for today's session. It's my colleague Leo Peberg. He's from product marketing and he will join us for the first part of this session today. And my name is Christoph. I'm from team trainings. Now, the topic for today is a very interesting one, I would say. It's about shading of PV systems and what we can do to avoid the hard impacts of shading, basically. And we have some very cool stuff to show you, some simulations as well, and quickly want to cover the causes of shading. And you might notice already, if you are in the system designing of such systems, it can be caused by simple stuff like roof structures or snow, dirt, leaves, chimneys, trees, the neighbor building, for example, and stuff like that. And we have basically a few myths that we want to clarify today. And how does shading affect yield after all? That's one of the major questions that we want to answer today. And the first topic that we always need to keep in mind is that intelligent system design and the efficient shading management that Fronius provides, for example, can reduce the losses to a minimum. And so we have some troubles with the slides because we cannot see the current slide, Christoph. We cannot see the current slide.
Just check it again. No, we just see the welcoming slide.
All right, we will do that. So now it should work.
Now it works.
All right. Thank you very much for the feedback. Now, okay, that's it for the introduction, basically. And I want to invite Leo onto the big screen. And yeah, we have some shading myths that you want to clarify for us, right?
Exactly. Thank you, Chrissy, for the introduction. Hello, guys in the audience. As you already introduced, basically there is shading is not a big deal anymore. So nowadays we have intelligent shading management integrated into the inverter. We have advanced module technology, and of course with a proper system design you can really avoid the biggest losses with a shaded PV system as well. But there are myths in the market since a long time. I heard them, I guess, 10 years ago, and nowadays, of course, this is not possible anymore or not realistic anymore, because on the myth is basically that the shaded module limits the power of all the other modules in the same string. So as you can see in this example, when you put one leaf on a module field, for example, then the whole string gets dragged down and the power losses are dramatically high, and that's totally not true anymore. This is a false myth, and why this is false, the solution is basically sitting in every module, and that's the bypass diode. A bypass diode is, as I said, standard in every nowadays PV module. Basically what we use now in the market is just half-cut modules, but it's also integrated in every standard modules. It's just sitting on a different position, but the bypass diode, or more than one, basically 3 bypass diodes are built in every PV module. So you have 3 diodes per module, 1 for each cell string. And what's very important, this is just a passive component. So the bypass diode is activated by a voltage drop or increment of the inverter. So the inverter is efficiently MPP tracking the whole power voltage curve and activating these bypass diodes, because the bypass diode, as I said, is a passive component and needs a voltage in reverse direction to get conductive. What is not a use for a bypass diode? Basically, the main purpose is to prevent hotspots, of course, which can, of course, also lead to a fire, but it also has the good effect that the current can skip over this shaded cell string when the bypass diode is activating, and all the other modules in the same string are then not affected at all. So you just lose this third of the PV module here. I can show it also with the laser pointer. Give me 1 second. So as you can see here, the 3 diodes on this module, when one diode is getting conducted conductive, then you just lose here one cell string, so 1/3 of the module, and all the other cell string of this module and all the other modules in the same string are not affected at all. That's a very huge topic to understand the impact of shading. How does a shaded standard module now behave in a partial shading situation or a heavy shading situation? Basically, what you can see here on the right-hand side is now again a PV module. We just took a normal 30 volt 10 amps module, so 300 watt peak module, where we have, for example, one cell shaded with a leaf or a hard shading. Also, when you put your hand on one cell, it would be the same effect. In this case, the inverter sees that the current of the string is decreasing dramatically, because when you put shading on a cell, then the voltage is not affected, but the current is affected. The current is limiting very, very heavily. And of course, when you limit the current, then it's true that the whole string gets limited with this current, because it's a serial connection of cells. It's basically PV basics, so to say. Now, of course, the inverter sees, okay, there is a huge reduction in yield losses. We need to do something. In this situation, now the inverter is then actively reducing the voltage to make the bypass diode conductive. The bypass diode needs, as I said, reverse voltage, so biased voltage, basically a negative voltage on the diode, and the inverter is reducing the voltage up to this limit that there's a negative voltage at this bypass diode. As you can see here in this example, you have here minus 0.6 volt at the diode, and it's getting conductive. So what is happening now? The full current is now bypassed through this diode and through the cell string. So not all the 10 amps are flowing through all the unshaded cells, but the 10 amps are split basically between the diode, and also some amps are going through the shaded cells as well. So it's pressed through the cell also. So it's basically split it up. But all the 10 amps of this module are going to the other modules in the same string, and there is no power limitation of all the other modules, and also no power limitation of this cell string and the right cell string. And that's the most important thing to know. This is the behavior of a shaded standard module. You have no yield loss in this case, or no heavy yield loss. You just lose the shaded cell string. You will now ask the question, okay, what you said in the beginning, half-cut modules is the nowadays technology. How does a half-cut module now behave in a shaded scenario? As you can see on the right-hand side, a half-cut module, the bypass diodes are basically sitting in the center of the module, and all the cells are basically cut in half and connected parallel. This has one major advantage in shaded scenarios. When you have, for example, a shading in the lower part or the upper part of the module, for example, the string is covered with snow on the lower part, then the top part of the module is still, or the current is still flowing in the upper part of the module. So in this case, for example, the inverter would not reduce the voltage to make these diodes conductive. You can see here they are gray, they are inactive, because the inverter sees, okay, there is still enough power flowing into the upper part, because it's a half-cut module. So in this case, the half current, so 5 amps, are still flowing, and you have a power output of 150 watt, which is the half of the PV module's rated power. If you would have this shading with a standards module, where what is not a half, where the cells are not cut in half, you would have 0 watts, because all 3 diodes would get conductive here, basically, to not limit the other modules in the string. Yeah, of course, we have to look in a bit more complex scenario, and that's the behavior in a string, because one module is one thing, but of course, in a practical scenario, we have also to look into the whole string, into the whole PV string. What you can see here is just an assumption of myself, a example with a PV system with 20 standard PV modules, where one module of 20 is shaded. For example, there is a leaf on one cell string, as you can see here again. Then the inverter is seeing, of course, we have some shading. The current is dropping tremendously. We have to do something. Again, the MPP tracking of the inverter is reducing the voltage of the whole string, in this case from 600 volts, so 20 modules, 30 volts, 10 amperes is 6000 watt peak power, and 600 volts of voltage, and the voltage gets, of course, decreased up to that point that again this bypass diode that, has a reverse voltage and it gets negative and conductive. The huge advantage, of course, the current can stay at 10 amps, so full current again, because it flows through this bypass diode, and the system output is then stays at 5,894 watts. So you just lose this one cell string because of the intelligent MPP tracking. If you would have no MPP tracking, then no bypass diode would get conductive. As I said, it's a passive component. The bypass diode would not be conductive, and in this case, the output power would be just 1,800 watts, meaning the voltage would stay at the same level, 600 volts, but multiplied with just 3 amps, so just the low current because of the shading. And this would, of course, be a tremendous yield loss, of course. So that's why we have an intelligent MPP tracking. What's now with this example with half cell modules, half cut modules? There are two examples. One in this case where you have an evenly shaded string, what you can see here. The best example would be, for example, snow. So the lower part of the module is covered with leaves or snow, but the whole string is basically covered with the same amount of shading. Of course, that's not the most common example, but there is, of course, there are scenarios where only the lower part is covered with snow, for example. Then you have the huge advantage of the half cut module, because the 5 amps, which are basically the result of the shading, the resulted 5 amps go through the upper part of all the modules. The diodes are not getting conductive because it's better for the inverter to not activate the bypass diodes, because you have 5 amps going through all the modules on the upper part, and you have half of the rated power of the string, so 3,000 watts. When you have a standard module, in this case, this would be 0 watts, because when you have the shading, all 3 bypass diodes would be activated, meaning all the modules would be produced 0 watts with a normal standard modules. So in different scenarios, I would really suggest to use half cell modules, because they have a better behavior of shading. Yeah, now the more common example, I would say, and that's the half cut module unevenly shaded, where you just have one half cell module shaded and the others are unshaded. For example, like you can see here in this module is shaded with some leaves on the bottom part. Then this module does not have an advantage to a standard module in this case, because of course in this case it's better for the inverter to make all 3 bypass diodes conductive. So to say, to kick out this one module completely out of the string, because all the other modules are producing a high power. And when this string would again be limited to the current of this module, meaning 5 amps, then this would be less yield than just kicking out this module. So again, the inverter is reducing the voltage to that amount that all 3 diodes of this module are getting conductive. In this case, this would be 568 volts. And then the current again can stay at the very peak, and that's 10 amps in the string. And then the system output is 5,682 watts instead of just 3,000 watts if there would be no intelligent MPP tracking or no bypass diodes getting conductive. So that's again basically the same scenario with a standard module, but without the tracking you would have again a very high yield loss. Yeah, that's basically the strategy, the technology behind this. I told you a lot of times that the MPP tracking of the inverter, maximum power point tracking, this is basically used in every modern inverter, but of course this control strategy technology differs from inverter to inverter. I guess Fronius has a very advanced MPP tracking, because we have a lot of experience in solar since 1995 with our first inverter, and this MPP tracking optimizes this output power of every PV module and string. So this power curve has always a peak at a specific voltage that you can see here, and that's the MPP voltage. And this tracker, this MPP tracker, begins with an increasing and decreasing the voltage. So it always tries to increase or decrease the voltage. And whenever the generated power at the inverter increases, as it gets higher, the algorithm continues to change the voltage in this direction to always increase the power. When the power on the inverter decreases, then the algorithm, the MPP tracker, changes the voltage into the opposite direction. of course, to then increase the power again. So that's basically how the algorithm is working, to shift the voltage in this direction that the power is on the maximum, so to say. But additionally to an efficient MPP tracking, we also have an integrated shading management in our inverter, and that's the dynamic peak manager. It's built into the inverter, but I don't want to tell you that much about it because my colleague Chrissy will now explain you a bit more about our Fronius dynamic peak manager.
All right, thank you very much, Leo. And yeah, now it's time for the Fronius inbuilt solution for that matter. It's the dynamic peak manager. And as we have heard, it's the same thing. We have an algorithm, which is a highly efficient tracking algorithm that is checking the entire power curve for the global maximum power point. So let me a little bit explain what the global maximum power point is. We have the schematic on the left-hand side here, and the blue curve would be an unshaded scenario. The red and the black curve would be a shaded scenario. And as you can see, in this kind of scenarios, we would have two power points, the local and the global maximum. And there is always one that is a little bit higher. And this point cannot be tracked without an algorithm. So the inverter would stick with the LMPP and would not check the rest of the curve for a higher output. And this is what the algorithm of Fronius does, the dynamic peak manager, and it does the checking every 10 minutes. So every 10 minutes, the full curve will be checked, and then on the global maximum power point, we operate again. Now, the cool thing about it is it's inbuilt, it's free of charge, and there is no additional components, sensitive components necessary, like optimizers or so. Yeah, we also have a simulation here ready to show, and that really shows the dramatic impact that we have with the DPM. So here you would see a system, a photovoltaic system, where we have shading from 8:45 to 10 o'clock in the morning. And in this time, we have this big cutout here in the yield. And of course, this would mean, yeah, high losses over the whole year, basically, if this shading is repeating itself every day. So this would be a solution without any algorithm, without any DPM. And with the dynamic peak manager, we see here the green curve, and this would result in a 7% increase or 7% more yield over the year with a free of charge system on board and without any additional components. So it really does make a difference. Yeah, and speaking of optimizers beforehand, and that we don't necessarily need them with the Fronius dynamic peak manager, there is also a question that we might want to raise here. Is the DC power optimizer a solution for such systems? Now, I quickly want to go through some points here that I've put on this slide. So the DC optimizer basically tries to optimize each and every module on the module level, not the string level, but really on the module level. It tries to operate on the specific MPP. Now that sounds pretty good in the first when you first hear it, but did you know that in some shading scenarios, for example, the bypass, the DC optimizer does nothing more than activating the bypass diode. So there is no really another advantage than we would have with a normal inverter. It really just activates the bypass diode, and that's it in some shading scenarios. Then if we would have no shading at all, we would have standby losses. Of course, in these kind of scenarios, the optimizer becomes a consumer. It needs energy. And more than that, we have multiple DC connectors or more DC connectors than with a standard solution. And we don't necessarily want that, because DC connectors, so MC4 plugs basically, are the main reasons for PV fires. They don't happen often, let me say that, but if they do, it's more or less the reason is the MC4 connections or connections at all. And if we use DC optimizers, we triple the amount of necessary MC4 plugs. So not a good idea actually. And last but not least, we would have efficiency losses due to voltage boosting or bucking. So let me repeat that once more. We have in some shading scenarios just the activation of bypass diodes with no further advantages than to a standard inverter. We have standby losses if there is no shading. We have the triple amount of DC connectors, MC4 plugs, and we have efficiency losses. So on the last topic, let me explain a little bit more about the efficiency losses. This basically means that there is a rated datasheet efficiency for such optimizers. And they are pretty high if you look at them. So like 99.5% at maximum or 98.5% weighted. So we are in the really upper part of this chart on the datasheet. Now, this would mean that we have the perfect input voltage of the system to the operating voltage of the inverter. Now, we need the perfect input voltage because this means the perfect efficiency of the inverter in order to get the correct AC voltage outside on the other side of the inverter. So we always need to back down or boost up the voltage to that certain input voltage of the inverter. And if we would have a very long string, for example, and all modules would be in series with the DC optimizer on them, this would mean that we need to back down. And this would mean that the operating range is dramatically decreasing, and also the efficiency of these optimizers would decrease because they only really work at the maximum efficiency at a rate of 1 to 1. And in other scenarios with shorter strings, with longer strings, you can see it in this chart here, we would come down to 96, 97% even. So there is really a decrease in efficiency depending on the string length of your system. All right, but that's enough for the DC optimizers. I quickly want to show a little bit more about some simulations that we've done with PV Sol and the Fronius system. Now, we have picked as location here Brandenburg in Germany. We have picked 30 half-cut cell modules from Trina Solar with 395 watt peak module power. They are all self-oriented, and we have an inverter here from Fronius, the Simogen 24 10 kilowatt. And yeah, there are 2 strings with 10 module each on the first MPP tracker and 1 string with 10 modules on the second MPP tracker. Now that's the basis of our simulation. And now we have put in some shading, some different scenarios, like a chimney and a tree. These are the 2 I want to show you today. Now, the results for the chimney simulation basically show us that there is 2 things happening. We have module-specific partial shading, which is basically a description for we are not getting the full irradiation on the whole module. Of course, because there is some kind of shading on it. And these kind of losses, they are permanent. We can't do nothing about it. Not even a DC optimizer or any kind of solution would resolve these kind of losses. They are just there because there is not enough irradiation on the module, right? So it's about 26 kilowatt hours that we lose here over a period of a year. 26 kilowatt hours. So 0.18%. It's not that big. And the second losses that we have is the mismatching losses that happen due to the configuration. Now, they happen because we have a configuration like a serial connection of modules, right? And like Leo mentioned beforehand, if one module is shaded, it could affect the other ones at least a little bit, because due to mismatching losses in the voltage leveling of the inverter. Now, they can be optimized, for example, with the dynamic peak manager of Fronius. And therefore, they are very strongly reduced to a limit of 0.06%, which would mean 8 or let's say 9 kilowatt hours over a year. So in total, we would have losses with this chimney structure of 0.24% over the whole year. So I personally would say that's negligible. That's really so low that you can operate like this, of course, as well. So here on top, we can see again, it would affect basically 2 of those modules with around 0.1% over a whole year. Right, and the second result of our simulation would be with a tree shading the system. And as you can imagine, a tree could have a little bit of a bigger shading than the chimney. And the results, again, are a module-specific shading and the mismatching losses. And both of them would be around 114 kilowatt hours and 32 kilowatt hours. But let me tell you again that the mismatching losses are very strongly reduced because of the inbuilt algorithm. So in total, we talk about 1% of losses, which are again very low compared to no algorithm, which would cause a very dramatic effect actually. Now, that's the 2 simulations. That's the webinar actually. We are at the end right now. And before I jump to the final slide, I quickly want to give you some seconds because we have a QR code inbuilt here. You will see more often in our webinars the inbuilt QR codes. And if you scan that, you will come right to our white paper selection, basically on our homepage, and as well the white paper, which is the topic of our webinar today about shading and dynamic peak management. So if you're interested, check it out. Scan the QR code and you will come directly to our list of white papers on the homepage. Now, a quick look to my colleague. Did we get questions so far? Not yet. Okay. Then I will jump to the final slide right now. Don't worry, you will find this webinar as well on YouTube in the upcoming weeks. And also the recording will be sent out to you so you can rewatch it anytime. Now, thank you very much for now, for listening, for joining us today. Thank you very much, Leo, for joining me today in this webinar. I hope it was interesting for you. If there are more questions, we will be online as usual a few minutes more, and you can send your questions in via the chat. We just mute ourselves for now and turn off the camera, and we will text you back if you have questions. Now, thank you very much again, and we see each other in the next webinar. Goodbye, guys.